we begin our discussion of section 2.1, algebraic properties of solutions. For the first time, we are talking about second order linear homogeneous equations. Second order means we have y prime prime. Please take a look at theorem 1. This is a so-called existence uniqueness theorem. This theorem says that if P of t and Q of t are continuous functions, then this equation with these two conditions, this initial value problem, has a solution. Moreover, this solution is unique. Here's what we do next. Take a look at what is written once again. We call this equation second order because we have y prime prime, homogeneous because we have 0 on the right, linear equation. Big question is, why do we call it a linear? By the way, you may ask me the same question here. We call this first order a linear differential equation. Folks, maybe somebody can tell me why we call this linear, why we call this linear again. Anybody?
Because the y is not squared or cubed, it's just to the power of 1.
Okay, so are you talking about this one?
Yeah.
Okay, very good point. However, imagine that instead of plus, we have times. Is this linear? And why? So you see, what you just said is true. Again, if instead of plus, we have times. However, if here we have times, this equation is no longer linear.
Okay, so these are functions of t. So whenever you multiply, that would make a t squared, in which case it wouldn't be linear anymore, right?
Well, note that q of t and p of t are some arbitrary functions. Here we can perfectly have t squared. Here we can have, say, sine of t. Nevertheless, we still call this linear. Why linear?
Is it because we only have two variables?
Two variables. But once again, if we replace this plus by times, the resulting new equation will not be linear.
Is it because of the linear operator?
All right, perfect. It's because the left-hand side is a linear operator. Next question is, what is an operator? So, please take a look at what is written over here. First of all, we can think about an operator as about a function of a function. Well, let us go back to pre-calculus. Note that we already discussed in pre-calculus a so-called composition of functions. F of g is called a composition of two functions f and g. We start with g, we act on g by f. For example, if f of x is x squared plus 1 and g of x is x minus 3, in order to find f of g, we replace x by this, by x minus 3. And therefore, you may ask a question, what's the difference between an operator and the composition of functions? Well, guys, in some sense, we use more tools to come up with a function of a function. Here's what I mean by that. Over here, y is an input. We act on y using the following tools. We add, we multiply by P of t, we multiply by Q of t. Then, in addition, we take the derivative. We've never done this before. Here, in order to come up with a composition of functions, we start with f of x, which is a function, and then we replace x by this. Here, as I said, we have more tools. In addition to standard operations, we allow to take derivative, or in general to take antiderivative. We act on y by some operator. And please take a look at how we denote operators. L, and then in square brackets y, and then in parentheses t, which means we act on y by L, where y is a function on t. Example, if over here P of t is equal to 0 and Q of t is equal to t, the whole thing becomes this. And therefore, in particular, if y of t is cosine, we replace y here and y here by cosine. We take the derivative, we simplify, here is the result. Or if y of t is equal to t cubed, we replace this and this by t cubed. We take the derivative, we simplify, here is the result. Folks, take a look at this. Think about questions.
It's just basically plugging into the original equation, right?
Yes, in order to find this, we start with a given expression and then replace this by a given function.
Right, thank you.
So we will be given P of t, Q of t, and Y of t?
Yes, so P of t should be given, Q of t should be given, Y should be given. But once again, this is not the only example of an operator. Let me give you a very simple example of an operator. L of y of t is equal to y. This is an operator. Or L of y of t is equal to y squared. So in other words, an operator doesn't have to involve derivatives. Well, next question is, what is a linear operator? Please take a look at this definition. An operator L is a linear operator if it satisfies two properties. Number one, L of cy is CL of y, where c is any constant, and L of y1 plus y2 is L of y1 plus L of y2. Question is, what is an example of a linear operator? Let us go back to our equation. In a moment, I'll show you that the left-hand side of this equation is a linear operator. In the same way, we can show that the left-hand side of this equation is also a linear operator. This is the reason why we call this equation a linear equation and this equation a linear equation. However, before I prove that this is a linear operator, let me show you an example of a non-linear operator. Here is the example. By the way, if you compare operators with functions, think about the following function. F of x is equal to x plus 1. This is a linear function. However, L of y is equal to y plus 1 is not a linear operator. How do we prove that this is not a linear operator? Well, a linear operator is an operator that satisfies both property number 1 and property number 2. Therefore, if our operator fails at least one property, this is not a linear operator. Let us show that this operator fails property number 2. By the way, one can show that it also fails property number 1. But as I said, it is enough to show that it fails one of these two properties. So let us show that it fails property number 2. We start with the left-hand side. The left-hand side is L of y1 plus y2. So, in order to jump from here to here, we replace y by y1 plus y2. Now, if we replace y here by y1 plus y2, we have to replace y here by y1 plus y2. It's exactly what is done here. So, according to what is written here, L of y1 plus y2, which is the left-hand side, is equal to y1 plus y2 plus 1. But now, let us look at the right-hand side. It's over here. Again, according to what is written here, if we replace y here and y here by y1, we will get this. So, according to what is written here, L of y1 is equal to y1 plus 1. Similarly, by this, L of y2 is equal to y2 plus 1. Now, 1 plus 1 is 2. Conclusion, L of y1 plus L of y2 is equal to y1 plus y2 plus 2. The left-hand side is not equal to the right-hand side, therefore L is not a linear operator. Folks, any questions here?
Can you explain how you got between those last two steps, like the L of y1 plus y2 to the next one below that?
No. These are two different steps. We do not deduce this from this or this from this. We do a totally different thing. In both cases, we use this formula. By this formula, this is equal to this. By this formula, this is equal to this, and therefore this.
Okay, yeah, thank you.
Folks, any other questions?
Could you explain how L of y1 is equal to y1 plus 1 again?
Are you talking about this?
No, the second one.
The second one. Okay.
Yeah.
So, start from here. In this formula, replace y by y1. We'll get the following. L of y1 is y1 plus 1. This is how we jump from here to here. Similarly, by this formula, L of y2 is equal to y2 plus 1. Note that this is equal to this. Done.
Oh, okay, I understand now. Thank you.
Any other questions?
And with that, at the first one, the L and the bracket y1 plus y2, that one, the y1 plus y2 would be representing just the regular y, right? And that's why you substitute y1 plus y2 into the other side of the equation.
Yes, well, think about normal functions. For example, if f of x is equal to x squared, we can replace x, say, by 3. F of 3 is equal to 3 squared. Or we can replace x by, say, 3 plus 2. Then f of 3 plus 2 is 3 plus 2, the whole thing, squared. See it?
Yes, yes, thank you. It's the same concept. It's just that like the variables kind of like make it harder to grasp, but I understand it.
All right. Other questions?
For the first one, can you explain why it's +1 instead of +2?
Over here,
Uh-huh.
well, once again, start from here. Replace y in both cases by y1 plus y2. If we replace this by y1 plus y2, we'll get this. If we replace this by y1 plus y2, we'll get this, and then plus 1.
Got it. Okay, thank you.
Other questions?
So a linear operator is like a specific kind of operator, right? So does that mean like the gradient operator is a linear operator?
Yes, gradient is a linear operator, yes. Next, let us go back to our equation. As I said, we can think about the left-hand side as about an operator. Here is the left-hand side of that equation. Let us show that this is a linear operator. In order to show that this is a linear operator, we should show that it satisfies property number 1 and property number 2. Let us start with property number 1. The left-hand side here is L of Cy. So let us replace y here, 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 and here by Cy. Done. Next, by calculus 1, when we take the derivative, we can factor the constant out. Done, done. Over here, we just switch positions. We put C over here. Done. Next step. C is a common term. Let us factor it out. Lastly, according to what is written here, this is equal to L of y. So L does satisfy property 1 because L of Cy is equal to C L of y. Now let us show that this L satisfies property number 2. We start from the left. L of y1 plus y2. We replace y here, 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 and here by y1 plus y2. Done. By calculus 1, derivative of the sum is the sum of derivatives. Here we just expand parentheses. Here's what we do next. Let us group together y1 terms. Done. And y2 terms. Done. According to this formula, this is L of y1, this is L of y2, everything is proven. Here, property number 1, and here, property number 2. Thoughts? Any questions?
So for the second condition of the linear operator, is it only 2 y's or is it just any general add-ins for y?
Well, once again, here is the condition. We just check this formula, nothing else. First, we check this, then we check this.
Okay, I guess that makes sense. Thank you.
All right. Next question is, okay, fine, we have a differential equation. homogeneous differential equation where the left-hand side is a linear operator. Why care about it? Well, guys, it turns out that if the right-hand side is 0 and the left-hand side is a linear operator, this is a big deal. Here is why. Please take a look at what is written here. So, this is a copy of equation 1. Suppose y1 and y2 are two particular solutions of this equation. We claim that c1 y1 plus c2 y2 is a solution again of this equation, no matter what is c1 and no matter what is c2. c1 and c2 are some numbers. By the way, we call this construction a linear combination of y1 and y2. So, in short, if y1 and y2 are solutions of this equation, then any their linear combination is a solution again. Why is that? Well, here's what we do. Solution means you replace y here, here, and here by this. You take the derivatives, you simplify, and you get 0. So let us replace y everywhere by this expression. Note that since we denote the whole thing by L of y, if we replace y here, here, and here by this, we have to replace y here by same expression. It's done. Next step. Note that we just proved that this is a linear operator. Therefore, by property number 2, L of the sum is the sum of L's. Also, by property 1, we can factor out C1 and we can factor out C2. Done. Here's what we do next. Y1 is a solution. What does it mean? A solution. This means that you replace y by y1, and after all simplifications, the result is 0. It's exactly how we jump from here to here. Since y1 is a solution of this equation, L of y1 is 0. Similarly, since y2 is a solution of this equation, L of y2 is 0. Lastly, obviously, C1 times 0 plus C2 times 0 is 0. So, if we replace y by this, which is over here, we get 0 again, which means this is a solution of our equation. By the way, if we do not use linear operators, we can easily prove same thing, but it will take a little bit longer. Let me show you over here. So let us go back to the appendix. Please take a look and compare. Here is how we prove same thing without linear operators. We replace y here, here, and here by this expression. We expand parentheses, we collect terms, we factor out C1, C2, we get 0. So this is why we care about this notation, about the whole concept of linear operators. We prove once that this is a linear operator, we denote it by L of y, then this knowledge allows us to prove this shorter. Folks, any questions here?
This is only if the differential equation is homogeneous, right?
Exactly. Excellent point. Here we use the fact that the right-hand side is 0. If the right-hand side is not equal to 0, we will not be able to jump from this to this. For example, if the right-hand side is 1, here we'll get C1 times 1 plus C2 times 1, which is C1 plus C2, which is not equal to 0, which is not equal to 1, which destroys our proof. So, in order to prove it, we use two things. Number one, the left-hand side is a linear operator. Number two, the right-hand side is 0. Other questions?
So are we going to use this to then be able to find that certain equations are solutions by breaking them down into that format of C1 Y1 plus C2 Y2?
Exactly. In a moment, we will use this piece of information in order to come up with the general solution of certain equations of this type. Because look, right now we know that we can construct infinitely many solutions using just two particular solutions. Question is there anything else? We will answer this question in a moment. Folks, any other questions?
Also, just a clarification with theorem 1, because it says that there's a unique solution, yet you assume two, I guess, different solutions for the linear combination part. That's only because theorem 1 has the prescribed initial conditions, right?
Yes, exactly.
Okay.
It's a very, very good point. Please don't confuse what is written here with what is written over here. Know that in theorem 1, we are not talking about this equation alone. Theorem 1 is about the initial value problem, means this in combination with this. If we combine this and this initial value problem has exactly one solution. However, if we consider only the equation, if we find two particular solutions of this equation, any their linear combination is a solution again. Other questions?
Wait, so does that mean, like, because we had two initial conditions for a second order differential equation, does that mean, yeah, and the solution yielded two constants? Does that mean the number of constants correlates with the order of the equation?
Well, yes, if I understand your question correctly, compare with first order. In first order, we have one equation, one condition. In second order, one equation, two conditions, in order to have exactly one solution.
Oh, I was asking, like, and by extension, does that mean, like, our solution would have two different, or not necessarily different, but two constants?
Well, we will discuss in a moment the general solution under certain conditions can be indeed written as C1y1 plus C2y2, and then since we have two initial conditions, these two initial conditions allow us to determine C1 and C2 uniquely.
Okay, yeah, that makes sense. Thank you.
All right, here's what we do next. Let us consider a particular case of this equation, namely this one. In our case, there is no y prime, means p of t is 0. And here we have just y, means q of t is 1. One can check that cosine is a particular solution of this equation. Well, just plug in cosine here. We have to find the second derivative. First derivative of cosine is negative sine. Second derivative is the derivative of the first derivative. Derivative of negative sine is negative cosine. So, second derivative of cosine is negative cosine. This is negative cosine. This is cosine. Negative cosine plus cosine is indeed 0. In the same way, we show that sine is also a solution of this. So, both cosine and sine are solutions of this equation. Therefore, according to what we just discussed, any their linear combination is a solution of this equation again. But now we can say more. One can show, and we show it over here, that this is not just a particular solution of this. This is the general solution of this equation. Question is, suppose we have some second order linear homogeneous equation, and suppose we have two particular solutions. Is it always true that C1y1 plus C2y2 is the general solution? No, the answer is no. Here's a very simple example. Think about this equation. Note that 0 is a particular solution of this equation. And now, replace cosine by 0. Y of 1 is equal to 0 is a particular solution of this. Y2 is equal to sine is again a particular solution of this. So both 0 and sine are particular solutions. But C1 y1 plus C2 y2 for 0 and sine is C2 times sine, because C1 times 0 is 0. Obviously, C2 times sine cannot produce, for example, cosine. So here's a very simple example of two particular solutions such that C1y1 plus C2y2 does not give us the general solution. Even simple example, y1 is 0, y2 is 0. Then y of t is 0. It's not the general solution. Conclusion. If we have an equation and we have two particular solutions, this does not necessarily mean that C1y1 plus C2y2 is the general solution. In which case, this is the general solution. Please take a look at theorem 2. Suppose y1 and y2 are two solutions of our equation 1. So here is equation 1. Here's what we do next. Let us consider the following so-called 2 by 2 determinant. 2 by 2 determinant is equal to this times this, which is over here, minus this times this, which is over here. Theorem 2 says that if after all simplifications this is not equal to 0, then indeed C1 y1 plus C2 y2 is the general solution. However, if this is equal to 0. What is written here is not the general solution. Let us go back to our equation. y1 is cosine, y2 is sine. Therefore, this 2 by 2 determinant becomes cosine sine, cosine prime, sine prime. Cosine prime is negative sine, sine prime is cosine. Now we apply this formula. Cosine times cosine, it's over here, minus sine times negative sine, it's over here. Minus times minus is plus. Cosine times cosine is cosine squared. Sine times sine is sine squared. And by trigonometry, cosine squared plus sine squared is 1. This determinant is equal to 1, which is not equal to 0. Therefore, this is the general solution of our equation by theorem 2. Last thing, if C1y1 plus C2y2 is the general solution, we say that y1 and y2 is a fundamental set of solutions. Moreover, we call this 2 by 2 determinant Wronskian of y1 and y2. With this in mind, we can restate theorem 2 in the following way. If Wronskian of two functions y1 and y2 that are solutions of our equation is not equal to 0, these two functions form a fundamental set of solutions. Folks, any questions here?
What was the difference between the fundamental and the general solution?
Here we say a fundamental set of solutions. This is a particular solution. This is a particular solution. These two particular solutions is a fundamental set of solutions if the set of all their linear combinations gives us all possible solutions of our equation.
And we knew it did because whenever we did the 2 by 2, it did not equal 0?
Exactly.
Okay.
By theorem 2, we know that these two functions is a fundamental set of solutions, meaning this is the general solution because the Wronskian, after all simplifications, is not equal to 0. Any other questions?
So as long as it equals anything but 0, then it's a...
Yes. If after all simplifications we get a non-zero number, this is the general solution, means y1, y2 is a fundamental set of solutions.
And then so do all second order equations have two like fundamental sets of solutions?
Not two sets, but if we have a second order linear homogeneous equation, and if we have two particular solutions such that this is not equal to 0, then this is the general solution. Folks, any other questions?
In a different problem, if we were to do the theorem 2 part, I mean, we basically know that cosine squared t plus sine squared t equals to 1. Would we have like a value of t to plug in to find a result?
Well, for some particular values, it can be 0. But please take a look at this. Unequal to 0 in this interval should be from some interval, not just at some point. So it's quite possible that there is no clear-cut trig identity or any other identity. This could be an expression on T that cannot be simplified down to a constant, and it's quite possible that this expression is equal to 0 at some particular value of T. However, it does not necessarily mean that this is not the general solution, because this is not the general solution only if this is equal to 0 for any T from an interval. Does this answer your question?
Yes, thank you.
Other questions?
So you can only use the Wronskian for second order linear homogeneous equations, is that correct?
Yes. By the way, going back to first order, note that if we skip C, this expression alone is a particular solution. With this C, what is written here is the set of all possible linear combinations. So in some sense, what is written here is a one-dimensional analog of this two-dimensional result, if you wish.
Could you kind of explain the intuition behind taking the determinant?
Okay, now this is not no.
Okay.
This is not easy. No. I can give you one example. Let us play with stuff. Let us go back. Remember I said that if we replace this by 0, then this is no longer the general solution. Let us see what happens to the Wronskian. If instead of cosine here and here we have 0, then the whole thing is 0, because the whole thing is 0 times this minus this times 0. 0. Here's another example. And by the way, this example previews a definition that we are about to discuss. Think about the following. What if instead of, say, sine, we have 2 times cosine? Our intuition tells us that 2 times cosine is very similar to cosine. Therefore, this new y1 and y2 will not give us the general solution again. Well, let us see what happens to the Wronskian. If instead of sine we have here 2 cosine, over here we'll get the following. Cosine 2 cosine, negative sine, negative 2 sine. And this times this minus this times this gives us 0. So particular solutions, cosine and 2 cosine, do not form a fundamental set of solutions.
So if it does equal 0, then what is it considered?
So once again, if this determinant is equal to 0 for any point T from this interval, y1 and y2 is not a fundamental set of solutions, means this is not the general solution. All right, so as we just discussed, if we replace sine by, say, 2 cosine, these 2 particular solutions do not form a fundamental set of solutions, because the determinant Wronskian is equal to 0. Please take a look at this definition. The functions y1 and y2 are said to be linearly dependent if one of these functions is a constant multiple of the other. two functions y1 and y2 are said to be linearly independent if they are not linearly dependent. Let us go back to cosine and sine. Let us prove that these functions are linearly independent. In order to show that they are linearly independent, we have to prove that cosine is not a constant multiple of sine, and sine is not a constant multiple of cosine. How do we prove it? Well, assume to the contrary that sine is a constant multiple of cosine. If we divide both sides by cosine, we will get this. But sine over cosine is tangent. This is a contradiction. Tangent of t is not a constant function. Similarly, if cosine is a constant multiple of sine, we divide both sides by sine, we get this. What is written here is cotangent. We got a contradiction again, because cotangent is not a constant function. So, sine is not a constant multiple of cosine. Cosine is not a constant multiple of sine. Therefore, these two functions are linearly independent. Example number 2. Let us consider two functions 1 and e to t. These functions are linearly independent because e to t is not a constant multiple of 1, obviously, because otherwise e to t is a constant. And 1 is not a constant multiple of e to t, because otherwise e to negative t is a constant function, which is not true. Now compare with example 3. Let us show that 0 and e to t are linearly dependent. First of all, observe that e to t is not a constant multiple of 0. y2 is not a constant multiple of y1, because e to t is not 0 times lambda. However, 0 is a constant multiple of e to t, because 0 is 0 times e to t. It's exactly what is written here. So, despite the fact that y2 is not a constant multiple of y1, since y1 is a constant multiple of y2, these functions are dependent. And now compare 3 and examples 1 and 2. Important. In order to prove that two functions are independent, we have to prove it in both directions. Meaning, we have to show that first function is not a constant multiple of the second function, and the second function is not a constant multiple of the first function. To the contrast, in order to show that our functions are dependent, it is enough to show that one function is a constant multiple of the other function. Let me show you how we apply this theorem. Please take a look at theorem 3. Theorem 3 says that two solutions, y1 and y2, of our differential equation are linearly independent if and only if they are Wronskian. is unequal to 0. Now, if we combine theorem 3 and theorem 2, we get the following corollary. Two solutions y1 and y2 form a fundamental set of solutions of 1 if and only if they are linearly independent on this interval. So, this corollary and theorem 2 give us two alternating ways of proving or disproving that y1 and y2 are a fundamental set of solutions. Way number 1, by theorem 2, we can find the Wronskian. Way number 2 is the corollary. According to what is written here, sine and cosine are linearly independent. Therefore, by the corollary, this is the general solution of our equation again. Repeat once again. Suppose we have two particular solutions of our equation. Question. C1y1 plus C2y2. Is this the general solution or not? Way number 1 is to find the Wronskian of these two solutions. If the Wronskian is not equal to 0, C1y1 plus C2y2 is the general solution. If Wronskian is equal to 0, C1y1 plus C2y2 is not the general solution. Now, way number 2. By the corollary, if y1 and y2 are linearly independent, C1 y1 plus C2 y2 is the general solution. If y1 and y2 are linearly dependent, C1 y1 plus C2 y2 is not the general solution. Now, questions.
So we only have to use like theorem 2 or theorem 3. You don't have to use both of them?
Exactly. You can use either theorem 2 or the corollary. Other questions?
If something is like linearly dependent, does that mean that like one of the lambda ones or one of the constants doesn't work or is incorrect?
If two functions are linearly dependent, in some sense, we just do not have enough material in order to build the whole building. Dependent means these two functions are very similar. It's better to say one function can be deduced from the other function by means of multiplication by a constant. Like here, these two functions are actually pretty different, but they are dependent because this is this times a constant times 0.
Okay, so how do you like check if something's linearly dependent? I guess it's a better way of asking.
So once again, we use the definition. Dependent means one function is a constant multiple of the other function. Here, note that 0 is indeed a constant multiple of e to t. Here's why. 0 is e to t times a constant, 0. So, step 1, use definition. Dependent means one function is a constant multiple of the other. This is what it means.
Right.
It's exactly what we see here. This function, which is 0, it's over here. This is y1, correct? So this is y1 according to this, This is y2 according to this, correct?
Okay.
We
Yeah.
see that y1 is equal to constant times y2. y1 is a constant multiple of y2. Done. Dependent.
Okay, so y1 is equal, or like one of the functions is equal to another times a constant. That's how you tell if it's linearly dependent, and then if else, then it's not, and it's independent.
Exactly. So
Okay.
if you see that one of the two functions is a constant multiple of the other, then dependent. However, in order to prove independence, you have to check it in both directions. You have to show that function number 2 is not a constant multiple of function number 1, and function number 1 is not a constant multiple of function number 2. See it?
Yeah, okay, I get it. Thank you so much.
Other questions?
Professor, what does the theorem 1 do?
Well, theorem 1 in this course is only of a theoretical interest, but actually it's a big deal. Theorem 1 says that if we have this differential equation and these two conditions, the whole initial value problem has a solution. Moreover, this solution is unique. It's a very important theoretical result. It does not allow us to find this solution, but it says that solution exists and unique. Any other questions?
So after solving, we would always have to find if it's dependent or independent, just to be sure we have the general answer, right?
Yes. So in order to find the general solution of this equation, number 1, find two particular solutions, and then there are two ways to continue. Either you find the Wronskian of these two functions, or you check whether or not these functions are independent.
Is the size of the fundamental set of solutions always going to be 2 for this case?
Yes.
Okay.
Yes, absolutely. So if we have second order linear homogeneous differential equation, then a fundamental set of solutions consists of two functions.